All right, today's lesson in modern biology is going to be our third class in modern biology. So this is our third class. On the study center, just make sure we don't get this confused. On the study center, this is going to be lesson 2. So we're getting into the content of lesson 2, but this is going to be our third class. All right, so for lesson 1, we had 2 classes. This third class, we're going to start lesson 2. The title of this lesson is Introductory Experiments in Chemistry and Physics, and I'll introduce you to this and we'll talk about it. So just get started preparing your notes. On your notes sheet, make sure you have your name at the top of the page, full name, first and last. Put today's date, March 30th, 2022. Title of the course up top is Modern Biology. And the title of this lesson, you could write Lesson 2, you could write Class 3, but the title is going to be Introductory Experiments in Chemistry and Physics. I'll write that up here in just a second. So the course, this is Modern Biology. Modern Biology. This is our third class, but we're studying the content of Lesson 2 in the online course. So this is our first study of Lesson 2. And the title of Lesson 2 is Introductory Experiments. Introductory Experiments in Chemistry and Physics. Okay, Lesson 2, Introductory Experiments in Chemistry and Physics. Now just to put this in context, and remember, your notes are proof of your attendance, that you were here for this class and that you paid attention and followed the teaching of this class. So make sure you take detailed, careful notes. We talked about high school science requirements. So let's just review this a bit because it'll help you to understand why we have a lesson about physics and chemistry in our biology class. We said that in high school science, a good college preparatory high school program will include 4 years of science studies. And I said, no matter what school you go to, there are 3 basic science courses in high school. The first is biology, which we're studying here. And then the second and third are taught in different order in different schools. Actually, all 3 of these are taught in different orders in different schools. Biology, chemistry, and physics. I might even list them in one video in a different order. There are 3 basic high school science subjects: biology, chemistry, and physics. We learned the definition of biology was the study of living things, right? We talked about how biology divides into 2 different parts, botany and zoology, and this textbook here adds the study of physiology. That's biology, the study of life. One thing I mentioned, I think in our first lesson, our first biology class, I mentioned that even though these are 3 separate subjects, they all work together, right? If you understand chemistry, you'll understand more about biology. If you understand physics, you'll understand more about chemistry. So they all work together. But we're studying biology first, and what stinks about studying biology first is that you haven't studied chemistry and physics yet. And knowing something about chemistry and physics will help you study biology. So what this textbook does, which is pretty smart, is it starts with a chapter that just introduces you to some basic ideas in chemistry and physics. Okay? So it gives you a little bit of chemistry and physics to help you get going. Basically, what you need to get going with the study of biology. All right, so the purpose of this chapter, I'd like you to write this down. The purpose of this chapter, which is titled Introductory Experiments in Chemistry and Physics, is to give you a little bit of knowledge of chemistry and physics that you can use in the study of biology. And I'll write that out. The purpose of this lesson is to provide an intro to chemistry and physics to help with the study of biology. Purpose of this lesson, lesson 2 in our textbook. The purpose of this lesson is to provide an introduction, just a little bit of introduction to chemistry and physics to help you with the study of biology. All right? Introductory experiments in chemistry and physics. To provide an intro to chemistry and physics to help you with the study of biology. Now, why is it important to have introductory experiments in chemistry and physics? Why doesn't it just say introductory information about chemistry and physics? Why introductory experiments in chemistry and physics? The answer is because, as the author has already explained, scientific knowledge comes through experimentation, right? So the textbook doesn't want to just give you information. That's really not how science should be studied. That's not how science should be studied. Make sure you're paying attention and taking notes. That's your assessment for this lesson. If it's true science, it shouldn't be studied like an encyclopedia. The method by which we gain scientific knowledge in modern sciences, the way that we gain knowledge is through observation, by conducting experiments. We just discussed that in the first lesson. And therefore, if we want to share some introductory lessons in chemistry and physics, and we want to actually practice what we just finished explaining in lesson 1, then we should do so through some introductory experiments. Okay? That would be the ideal way to study the natural sciences, by experiments. The problem with experiments is that they take a lot of time and they can be expensive if you have to buy supplies, right? It's often not realistic to actually carry out experiments. But one thing that's helpful and one thing that I recommend to you is you can simply study experiments. Like these experiments we're going to look at in this lesson, they're not too complicated. They're not mysterious. You don't need to actually see these things and do these things to understand what the experiment shows us. Okay? So if I said you need to conduct an experiment and hold a piece of paper over a flame and see that fire burns paper, you don't need to go and start a fire and get paper and see. There are some experiments which we can understand them by simply reading about the experiment. There are other experiments which you might not even believe it's true unless you do it yourself. Okay? So we have to make judgments in those things because there's only so much time. But that's the purpose of this second lesson, to introduce us to some basic ideas, basic concepts in chemistry and physics, which will be helpful to us as we get started in the study of biology. So what I'd like to do now is just read a bit of this chapter. We'll go nice and slow, and then we'll summarize it on the board to help you with your notes. All right? Introductory experiments in chemistry and physics. In the introductory chapter, we learn that science concerns itself with matter. And you should ask yourself, what is matter? We said matter is any sensible material, right? And I made a note in our first lesson that we have to make sure we remember in natural sciences that air is material. Air is not empty space. There's all kinds of stuff, all kinds of matter in this air, even though it's invisible, even though it doesn't smell right now. There's all kinds of stuff in this air. It's not empty space. We learned that science concerns itself with matter, doesn't have anything to teach us about things that are not material. And that the science of biology is concerned with the study of matter when it is in a living state, living matter. We could say biology is the study of living matter. In order to understand this definition, we must first get a conception, get an idea of what matter really is. So before we can understand that definition, that biology is the study of living matter, we need to make sure we have a clear understanding of what matter or material is in science. In this first paragraph, or the next paragraph in our textbook, describes matter, and I'll read it for you. So pay attention. Remember, all scientific knowledge, all true scientific knowledge comes through observation of material things. If you take a piece of ice in your hand, you are aware that it's cold. You're also aware that it has weight. You can feel that it has weight, and by looking at it, you can see that it has a certain form or a certain shape. We call it a solid, and we talked about this, in geometry class, right? A solid is a three-dimensional body, right? A piece of ice in your hand, you can immediately, by your senses, start to collect information about that piece of ice. You can feel that it's cold. You can feel that it has weight to it. And you can see that it has a certain figure or form or shape. You can see it has 3 dimensions. It's a solid. A few minutes of exposure to the warmth of your hand will change this solid into a liquid. The ice will melt. This is obvious. We all know this. But what the textbook is trying to get you to do is think about what's happening in your hand with this piece of ice. As soon as you take this piece of ice in your hand, it begins to change. It's a solid when you take it out of the freezer. You can feel that it's cold. You can feel that it's hard and that it has weight. But as you hold it in your hand, this piece of ice starts to interact with your hand, and the heat from your hand starts to change that matter, starts to change the ice. In a few minutes, the warmth from your hand will change this solid into a liquid. If you were to collect that water that was ice and turned into liquid water, and you were to put it into a pan or a jar and put it on the stove and heat it up, it will boil and will change again. It will change from liquid into a gas. The water in the pot will disappear, and you'll be left with an empty pot. So from the freezer as a solid piece of ice, to melted water, to evaporated gas, that piece of ice will continue to change as the circumstances around it change. Over the flame it will boil and will be changed again, this time into a gas, which passes off into the air and becomes invisible. We don't think about this scientifically, but you can turn a solid piece of ice into invisible air by heating it. And everything that was present is still present, but it's changed its state. The ice is successively changed from a solid into a liquid and then into a gas. In each state, we could measure it and weigh it. We could weigh it and measure it as a solid. We can weigh it and measure it as a liquid. We can weigh it and measure it as a gas. In each form, it occupies space. It must be considered matter whether it is in the form of a solid or a liquid or a gas. That's why it's important for us to remember that air is matter, because air is not empty space. So, just to summarize this quickly, when we talk about matter, we understand that matter can exist in at least 3 different states. So this is called the states of matter. And it helps us to understand what matter is. It's easy to understand. It's easy to understand that matter can be solid, like an ice cube, like a piece of metal. The same thing will happen to metal. What happens if you heat metal? Same thing, right? The ice cube starts out in a state of matter called a solid. It then is heated and changes. It doesn't change its matter. It doesn't change what it is. It's still the same substance, but it changes the state. It changes to a liquid. And when boiled, the water does not change. It changes its state and becomes a gas. So these are called the 3 states of matter, the 3 different states in which matter can exist at any time. And it's important to realize that a gas is matter, and what we mean by gas. A gas can be invisible. Normally gases are invisible. But that ice cube can move from a solid into a liquid to a gas, and it can be converted back into liquid and can be converted back into solid. If we boiled that water, but we put a cover, just think about it, when water is boiling in the pot and there's a cover on the pot, what happens? That the water boils, it evaporates as gas, but then it hits the lid of the pot, cools down, and turns back into water. Right? We could collect that water. Take the water, put it back in the freezer, and turn it back into ice. So we can control that water and turn it through all its states from one into the other, back and forth. All right? It's all water, but water in different states. Okay? So we need to make sure when we think of matter, we don't just think of solids as matter. Material is not just rocks and dirt and wood. It's also liquid, but it's also gas. And like I said, in this air, in this room, it's not empty space. You have no idea what's actually in this air right now. You have no idea what's in this air. Okay, when I talk, there's gas coming out of my mouth, carbon dioxide, that's entering into this air. And if we sat in this room and this room was closed off and we kept breathing and talking or just breathing, we would actually change the gas in this room and it would go from a room with oxygen to a room that was increasingly filled with carbon dioxide, and it wouldn't be healthy for us to be here. We would need some fresh air. Okay? So anyway, the point of this is that matter can pass through 3 states, solid, liquid, and gas. Let's go on in our study here, in our textbook. The next section is titled Physics and Chemistry. You should outline the sections we go through. The first section was titled Matter. We talked about the states of matter. You probably already have that in your notes. This next section we're going into is titled Physics and Chemistry. Physics and Chemistry. The sciences which treat chiefly of the properties and forces of inorganic or dead matter, the sciences which treat chiefly, that means they don't treat only of dead matter, but chiefly with dead matter, and of the relations of the parts of substances that compose it, are known as the sciences of physics and chemistry. So in this section, we have a description. I wouldn't call that a definition, but it's a description of physics and chemistry. And I'll repeat that. The sciences which treat chiefly of the properties and forces of inorganic or dead matter. Physics and chemistry are unlike biology, because biology is the study of living matter, organic matter. Physics and chemistry chiefly study inorganic matter. So physics and chemistry are concerned with a different kind of matter. There's living matter we study in biology. Inorganic or dead matter we study in physics and chemistry. In that, really just a sentence there, it says, we study the properties and forces. Properties means characteristics, learning about inorganic matter. Forces means different influences or causes of motion and activity that take place. Like gravity would be considered a force. But it also says the relations of the parts of the substances that compose it. So in physics and chemistry, we don't only study whole things that are inorganic or dead, we also seek to analyze or break them down and study the parts of different substances. And those sciences are physics and chemistry. Okay? We seek to understand the parts, how things are actually built. The title of the next section in your book is Chemical Element. Chemical Element. Chemical element. Listen carefully. All the building materials of this universe, living materials and lifeless materials, all the building materials are classified by chemists as either chemical elements or chemical compounds. So chemists all the building blocks of matter are classified by chemists as either chemical elements or chemical compounds. A chemical element cannot be broken down into a simpler substance. So a chemical element is a simple substance. A simple substance that cannot be divided into a simpler substance. Okay? Notes. A chemical element is a simple substance. If you understand that idea of simple substance, that's the easiest way to describe it. It's a simple substance. A chemical element is so simple in its structure that it cannot be broken down or decomposed into a simpler substance. It's as simple as it can get. So if we have a substance that is as simple as it can get, we can refer to that as an element, a chemical element. Examples of such substances, examples of elements, are oxygen, nitrogen, carbon, and there are many others. And it's important to note that these are chemical elements. Oxygen, nitrogen, carbon, and there are many others. I think chemists have identified over 100 chemical elements. The number changes. Some chemists disagree on the number. Some substances are considered as elements that aren't actually natural. They're actually man-made elements. So those issues get kind of confusing. So you should understand what a chemical element is. It's a substance that is simple and cannot be broken down into a simpler substance. So if you were to ask, what is a piece of wood made of? And you were to break down the wood into all of the chemical substances that are present in the wood. If you take a piece of wood, is there water in the wood? Yes, there is, right? Is there air in the wood? Yes, there is. And is there solid material in the wood? Yes, there is. Could it be different kinds of solid material? Yes. And so a piece of wood, you can just refer to it as wood, but it's actually a compound. It's composed of a number of different chemical elements. And one thing that chemists do is they study substances like wood and everything else, and they try to break it down and figure out what chemical elements is this made up of. All right? So that's part of what chemistry studies. It seeks to identify the elements. We'd like to know all the elements that exist, all the building blocks that exist in nature. So one example given to us in our book is oxygen. Oxygen is an example of a chemical element, oxygen. 1/5 of our atmosphere is made up of oxygen. 1/5 is 20%. So if you think about the air around us in our atmosphere on Earth, 20% of that gas that surrounds the Earth, 20% of the gas, all mixed up with other gases, 20% of that gas is oxygen. Not 100%. If you think we need oxygen to breathe, but the air isn't oxygen. Oxygen is just one element in the air, mixed up with other elements. So an example would be oxygen. Another example would be nitrogen. Most of the rest of the air we breathe is nitrogen. Oxygen and nitrogen. Carbon is another example of an element. Carbon. All living things, all physical living things, all material living things contain carbon. When you burn a piece of wood, the ashes that are left over are mostly carbon. the water boils out. You know, when you throw a log into the fire, you see the water boiling out of it, right? Air that's inside the wood is released through the fire. And when the whole thing burns up, the next day you go out and you look, and there's just this weird pile of ash that's left behind, right? The other elements are separated by the fire. They go to their places. And you're left with some substance. And you see, you might be interested to know, what is that substance that's left behind? Well, it's mostly carbon. So carbon is another example. So you have 3 examples given in the textbook: oxygen, nitrogen, and carbon. Over 60 other chemical elements of more or less importance to us exist in the study of biology. And like I said, that number of elements, it's changing often as chemists continue to study and believe that they discover new elements. The number's over 100 now, and it'll change. If you go from one website to another and ask how many elements are there, the numbers will change, okay? That's really not important. So understand what a chemical element is. Do you have a good idea of what a chemical element is? Right? And you have a couple examples of chemical elements, and we can name many more. Gold, for example, is a chemical element. Iron is a chemical element. Lead is a chemical element. So there are many chemical elements you're familiar with. Some of them you actually can see. Some of them you can handle and have seen before. Others of them are mixed up with other elements and you never see them in their pure form. All right? But the building blocks of material, of matter, the building blocks are called chemical elements. Substances that cannot be broken down into simpler substances. The simplest substances are called chemical elements. Moving on in our textbook. So, after introducing the idea of a chemical element, you could ask yourself, well, this is science class, right? This is science class. I'm not supposed to just be told what to believe. I'm not supposed to be told what to believe in science. This is not a religion. So how can this biology textbook tell me about oxygen and nitrogen and carbon? I have no way to know if that's true, right? I thought science was supposed to be learned through observation. Well, that's the purpose of this chapter. So what this chapter does is provide for us a number of simple experiments. Now, you could actually do these things if you want to, just to see them. All right? If you'd really like to see these experiments, but some of them are pretty simple, and you may have already experienced them before just in ordinary life. So at the top of the next page in our textbook, we're introduced to a simple experiment that proves to us that oxygen exists. So here's a little experiment that's described in your textbook. Oxygen may be easily prepared. You can actually separate oxygen and contain oxygen, the element by itself. Oxygen may be easily prepared in a classroom or at home. So you want some oxygen? You can prepare yourself some oxygen, and here's how. Now it gives you some chemicals that you would need, and you can buy these chemicals from a chemistry supply store. Remember, I worked in a chemistry lab. So in our chemistry lab, we had cabinets and cabinets filled of chemicals that were used in experiments. And I had to go to work every day, and I had a list of things I needed to do, and I had to weigh out different quantities of different chemicals, put things together, make mixtures together to do and test different things in the chemistry lab. There are chemistry supply stores that will sell you containers of chemicals to use in chemistry experiments. So the experiment here says to take half a teaspoon of black oxide of manganese. It's something that you could buy. You can order it on Amazon. Take a half a teaspoon of black oxide of manganese. Manganese is an element. With a little more than its bulk of chlorate of potash or potassium in a test tube. And just so you know, in chemistry, a test tube is a small glass tube that is fireproof. So you can put it over a flame, you could heat it, you could put it in a freezer. A test tube, a small tube. So put a half a teaspoonful of black oxide of manganese and a little more than its bulk of chlorate of potash or potassium in a test tube over a Bunsen flame. A Bunsen flame in a chemistry lab is a little gas burner. So you can just turn on the gas, light the flame, and you've got this little gas flame that you can use to heat things up. It's called a Bunsen burner. So heat this mixture up over a Bunsen flame. Vapors will be seen to rise as the mixture becomes heated. After a moment, insert a glowing match into the mouth of the test tube. It will burst into a bright flame. And then we're asked, in what form does oxygen pass off from the two chemicals in the test tube? The answer is as a vapor or a gas. How can you determine the presence of oxygen in a substance? Oxygen is flammable. That's one way to tell that it exists. So the vapor that will be released will be oxygen. Okay? You could collect that oxygen, but by sticking the glowing match into the test tube, as the vapors come off, it ignites because that vapor is oxygen and it's flammable. And when the warm match is put into the test tube, it bursts into flame. Okay? So it's an example to prove that there is actually a substance in the air that's not just regular air, because it's flammable. If I strike a match and the match burns because there's oxygen present and it allows the fire to burn. If you want to put a candle out, you don't need to blow the candle out. All you need to do is put a cover on the candle, and as soon as the oxygen in the candle jar is burned up, the flame will go out because there's no more oxygen. All right? So that's an example of an experiment that allows you to prepare oxygen, to prove that there's actually some element, some chemical present in that vapor that's not just ordinary air. All right, so that's an experiment for the preparation of oxygen. Now, the next section, which I'd like you to take notes on, is titled The Properties of Oxygen. So let's study oxygen a little bit. What is oxygen? And remember, this is not chemistry class, so this is not some kind of exhaustive study of elements and compounds and experiments in chemistry. This is just an introductory set of experiments to give us an understanding of matter so that we can study biology. The next section is titled Properties of Oxygen. So what are some properties of oxygen? What are some properties of oxygen? The physical properties of oxygen are those which we determine with our senses. So the only properties that we can speak of in science are physical properties, things that we can sense. So how do we determine the properties of any substance? We set our senses to work on it. We smell it, we look at it, we feel it, and so on. We could taste it. Might not be a good idea, but even smelling it might not be a good idea, right? You can make yourself sick. But we use our senses to learn about the properties of different substances. because they're physical, they're material substances. Oxygen, when carefully prepared, so if you actually can obtain pure oxygen, oxygen is colorless, odorless, and tasteless. So let's just make a list. Colorless, odorless, and tasteless. Colorless, odorless, and tasteless. Well, that stinks, right? How in the world am I supposed to identify oxygen when it has no color, no odor, and no taste? No color, no odor, and no taste. It's clear, I can't smell it, and I can't taste it. How then can I know it even exists? Are these chemists just pulling our legs? How do we know oxygen even exists? It's colorless, odorless, and tasteless. It is known to form nearly half of the Earth's surface. It is known to form 8/9 of all water and over 3/4 of the weight of the plants and animals inhabiting this world. But it's colorless, odorless, and tasteless. How do we know it exists? Here's how. It has the very important chemical property of causing things placed in it to burn. So the important chemical property of oxygen is that it causes things to burn. That's how we can know that it's present, even though it's invisible. We can't smell it and we can't taste it. If it's present, something will be able to burn. If it's not present, something might not be able to burn. So it has this very important chemical property of causing things to burn. If, for example, a piece of wire is heated red hot, so you heat up a piece of wire so it's red hot, and if you place that heated wire into a jar of oxygen, the metal will burn with a bright flame. The oxygen will allow the heated metal to burn, to burst into flame. Okay? So how do we know that oxygen is present? Flammability, right? Something can go on fire. That's how we know that oxygen is present. We then learn an important term called oxidation in this chapter. We're at 43 minutes, so we'll probably get through this lesson on oxygen and then stop for lesson 2. Oxidation is a term that we're introduced to in this lesson. What is oxidation? Oxidation. So we've learned that oxygen is crucial to fire, right? To things burning. If you've seen fire, you've been in the presence of oxygen. Oxidation is another way that we can see that oxygen is present. So let's learn what oxidation is. We have a little experiment. Light carefully a small piece of magnesium wire and then place it in a test tube in which you have previously prepared some oxygen. Now, you might wonder, how in the world can I put a piece of wire in a tube? A test tube is open, right? It's shaped like a U. It's open. How in the world can I contain gas in a test tube? Well, there's two ways. One is obviously to put a stopper, like a rubber stopper, in the test tube. That would contain it. But then how could I put a piece of wire in it? That doesn't make any sense. Well, you can contain gas like oxygen in a test tube by turning it upside down if the air rises, especially warm air, right? So there's a couple of different ways to contain a gas in a test tube. But put a heated piece of magnesium wire into a test tube in which oxygen has been prepared, and you will see a very bright flame. A light-colored ash will be left behind. This ash that's left behind is magnesium oxide. In the above experiment, the oxygen in the test tube unites with magnesium so rapidly as to form a flame. This process is known as a combustion. So the process whereby something bursts into flame is called combustion. You've heard the word combustion when we talk about engines, right, in cars. You've heard about a combustion engine. What does that mean? It's an engine that's powered by explosions. That's what combustion means. When something bursts into flame, that's combustion. So what is oxidation? What is oxidation? The chemical union of oxygen with any other substance is called oxidation. So what is oxidation? Oxidation, let me get this in your notes. Oxidation is the chemical union of any substance with oxygen. Oops, not Q. Oxidation is the chemical union of any substance with oxygen. The chemical substance of any substance with oxygen. So in that experiment that was just described, when that heated piece of magnesium wire was put into the tube of oxygen, it burst into flame, and ash was left behind, and that ash was called magnesium oxide. That means it's a substance. Magnesium oxide is a substance that's composed of the combination of magnesium with oxygen. It's oxidized. Oxidation is the chemical union of any substance with oxygen. All right? So when we make a compound, when we make a chemical compound, and one of the elements in that compound is oxygen, when we make a compound with oxygen, that process is called oxidation, when a substance is chemically joined together with oxygen. All right? The chemical union of oxygen with any substance is called oxidation. Oxidation takes place wherever oxygen is present. Wherever oxygen is present, oxidation takes place. So this answers the question, how do we know oxygen is present if it's colorless, odorless, tasteless? How do we know that it's present? One of the ways that we know it's present is by oxidation, because it causes things to change. It causes change. One of the ways we know oxygen is present is because we see the effects of things being joined together with oxygen. We see the effects of oxygen. That's one way we know that it's present. We saw before an important chemical property of oxygen is it causes things to burn. So we recognize oxygen is present by its effects. Oxidation takes place wherever oxygen is present. These facts, as we shall see later, have a far-reaching significance in the understanding of some of the most important problems in biology. All right, so how do we know oxygen is present? We can't necessarily see it, we can't smell it, we can't taste it. We can see its effects. It causes things to burn, and when other elements are joined to it, when other substances are joined to it, it causes a process that's known as oxidation. All right, we're presented next in our textbook with a third experiment, one that you're all familiar with. If you light and burn a match, you experience oxidation. Okay? This experiment, and realize experiment doesn't necessarily mean something that's formal and set up in a laboratory. It just means an observation, right? You prepare and carry out some observation. Oxidation in a match. The simple process of striking a sulfur match. So I have some matches right here on my desk. You see that the tip of a match is coated with some substance. Okay? That substance is sulfur. All right? It's a specific substance. The simple process of striking a sulfur match gives us another illustration of this process of oxidation. The head of the match is formed with a composition of phosphorus, sulfur, and some other materials. Phosphorus is a chemical element distinguished by its extreme inflammability. That means it doesn't burn. Phosphorus doesn't burn. It unites with oxygen at a low temperature. Sulfur is another chemical that combines easily with oxygen, but at a much higher temperature. The rest of the match head is made up of red lead, and this might refer to a different kind of match, or some other substance that will release oxygen, and some glue or gum to bind the materials together. The heat that's caused, so the reason why we rub the match on this sandy side of a box, the reason we rub it is to create friction, because when we create friction, it's a way of generating some heat. That's why we rub it, to create heat by rubbing, just like when you rub your hands together to warm them up. By striking the match on the box, we introduce heat to that substance on the tip of the match. When we rub that match on the matchbox, the friction causes heat, and it causes the phosphorus to ignite. This in turn ignites the sulfur, and the sulfur in turn ignites the wood of the match. I have to clarify one thing there. On that previous sentence, it said that phosphorus, I just want to clarify one thing. The textbook says that phosphorus is a chemical element distinguished by its extreme inflammability. Inflammable would appear to mean not flammable. But here it says that the phosphorus actually lights first, right? So what I think is that if you look up the word inflammable, you'll find that it has another meaning where it actually means the opposite, where it means it actually is flammable. So just make a note of that. I think by inflammable there, they actually mean the opposite, because in the experiment here, it tells us that the phosphorus ignites first. It's more flammable, more easily flammable, okay? So when we strike the match, the phosphorus ignites. That produces more heat. That causes the sulfur to light. That creates more heat, and that actually lights the wood of the match. It's like when we start a fire in the fireplace. We start with paper, then sticks, then wood, right? The paper ignites easily. That starts to get hot. It sets the sticks on fire. They get hot. They get hotter than the paper. And then the burning sticks sets the firewood on fire. And we have to sort of get up to the heat needed to make the log burn. That's how a match works. The different chemicals in the match light, and eventually they get to a heat that's hot enough to set the wood of the match on fire. Okay? So finally, the wood of the match ignites. The wood of the match is composed largely of the element carbon. So now we have carbon involved in this. And that's lighted by the fire and oxidized. Oxidation takes place. If we could take out the different chemical elements of which the match is formed and oxidize them separately, we should find that the amount of heat needed to start the oxidation of the substances would vary. The element phosphorus is kept under water in a glass jar because of the extreme readiness with which it unites with oxygen. That's why I said before, inflammability. That's either a typo or they're using inflammability to mean flammable. That's possible. Phosphorus is very flammable. So it's good that we caught that one bit of confusion there. The element phosphorus is so flammable that it has to be kept under water in a glass jar so that it doesn't ignite. Okay? So even in striking a match, so now we know how that process works. We strike it to create friction. Friction creates a little bit of heat. That little bit of heat is all that's needed to make the phosphorus ignite. The phosphorus ignites, and that causes the sulfur to ignite. And the fire gets a little hotter, and then it's able to ignite the wood, which gives us the heat and the flame that we need with a simple striking of a match on a box. Okay? We can have a fire in our hand and have it be safe and comfortable by using other chemicals to create a flame under control. We're at 57 minutes. We're going to read one more section and then wrap up here. There's a second experiment with regard to oxidation. So we've seen oxidation in the lighting of a match as different chemicals unite with oxygen by the addition of heat. So the heat, what I want you to see is the heat added to the substance causes it to react with the oxygen in the air and ignite. Okay? That's the process of oxidation and combustion. Oxidation may take place with very little heat present, although heat is always the result of oxidation. Oxygen causes substances to burn. One result of oxidation is it produces heat. Heat is always a result of oxidation. Take an iron nail and place it into a bottle of water and seal the bottle. Take a nail, put it in a bottle of water, and seal the bottle. What do you think will happen to the nail in a bottle of water? You think it will rust? Will the nail rust in the water? This is the purpose of this experiment. Many people think that water causes metal to rust, but does it? Well, that's the purpose of this experiment. Place an iron nail in a bottle of water and seal the bottle. Why do you think we seal the bottle in this experiment? To let no oxygen get in. So if we have a nail, an iron nail in water, underwater, with no oxygen, so we seal it so that no oxygen can get in. We have iron and water. Does water cause rust? This experiment will show us if water is the cause of rust. All right? So the iron nail is put into the bottle in water and sealed. Another nail is placed in a saucer or a dish. Another nail is placed in a dish with a little bit of water. Rust will form on the nail in the saucer, but not on the nail in the bottle of water. So does water cause rust? It's necessary in forming rust, right? But it's not the cause of rust. What happens when metal rusts is oxidation. The metal is united with oxygen. Okay? Note the formation of rust on the nail in the saucer and the absence of rust on the nail in the bottle. Rust is iron oxide. That's what rust is. So if you take an iron nail and rust forms on that nail and you scrape that rust off into a test tube, you have a chemical compound called iron oxide. It's formed by the union of iron with oxygen. And it's a different substance. It's called iron oxide. Rust is iron oxide formed by the union not of metal with water, but of iron with oxygen. This kind of oxidation is said to be slow oxidation. Slow oxidations are constantly taking place all around us in nature and result in the process of decay, breaking down of complex materials into simpler materials. So oxidation is taking place all around us. How do we know oxygen is present in the air? By its effects, by oxidation, right? If there was no oxygen, my match would not light. My fire wouldn't burn. The nail wouldn't rust if there was no oxygen. Things wouldn't break down. A dead tree wouldn't decay and break down and return to the soil. So we can tell that oxygen is present by its effects. It's colorless, it's odorless, it's tasteless, but we can tell it's present by its effects. Okay? The last piece, there's just one little bit left. I might as well get it, and we'll be finished in this lesson with oxygen, okay? The last point is that heat is given off as a result of oxidation. Heat is given off. Now, sometimes, obviously, that heat is very great, right? In a fire, the heat given off is great by oxidation. If we get a paper fire going, it'll get hot in here quick because oxidation is taking place, rapid oxidation, not slow oxidation, rapid oxidation, and oxidation is giving off heat, and we can feel that. Heat is given off through oxidation. One of the most important effects of oxidation lies in the fact that when anything is oxidized, heat is produced. So another way we can tell oxygen is present is the production of heat through oxidation. This heat may be of the greatest use. Coal, when it is burned, anytime something is burned, we can just say it's being oxidized. That's what we're actually doing. By burning things, we add heat artificially. When something is heated up, it allows it to join, to unite with oxygen, to be oxidized, right? We allow this process of oxidation to begin, and it gives off heat. We can produce heat the way we want it, like we do in a house. So heat is produced. When coal is burned, coal is oxidized, it gives off heat. The heat can boil water in tubes of a boiler. Steam can be generated, and steam can be used to turn the wheels of an engine and perform work. So we can actually use the process of oxidation to do things. This is talking of the time when coal was used to power trains and engines. The energy that's released by the burning of coal can be transformed into any kind of work power. Energy is the ability to perform work, and that's the end of this this paragraph where we're going to cut off for this lesson. So in this third class, we've started this lesson on this introductory experimentation to see some of the principles of chemistry and physics. We talked about the fact that substances that exist in nature, we talked about matter, how it exists in different states. And we said that the substances in the natural world can be broken down into simpler substances. And when we can't break substances down anymore into simpler substances, those simple substances are called chemical elements. Our textbook is leading us through some experiments that allow us to see that there are different elements present in different substances. The first one we looked at was oxygen, and we learned about oxidation, how oxidation relates to fire, how oxidation relates to rust, how oxidation relates to decomposition, things breaking down. All right? So we learned some of the properties of oxygen. Oxygen is colorless, odorless, and tasteless, but we can tell it's present by its effects. It causes things to burn. When chemicals unite with oxygen, that process is called oxidation, and heat is given off by that process. Different substances are formed as other substances react and are joined together with oxygen. All right, so we're going to cut off there with this lesson in our introductory experiments in chemistry and physics. In our next class on biology, we'll pick up there. The next topic is carbon, so we'll get into the study of carbon in our next lesson.